From sigma to integrals. How do we go from this rectangular area approximation to an exact value of the area? So we have here this graph. This is an f prime graph, and underneath it we have these rectangles. And each of these rectangles is going to be the height of the graph, which is the f prime value, times the delta x, which is the width. And if we sum up all these rectangles, we can approximate the area underneath this curve. So we can make this Riemann sum approximation better and better by making the delta x width smaller and smaller. So how do we do that? Well, we're going to let the delta x go to 0. If we take a look at the interval width here, we could make an expression for the delta x. So we're going to just call that the interval width I, and that's just going to be the difference between a and b. So b minus a represents our interval width. So we take a look here. We have the interval width in purple, which is b minus a, the n minus the starting value. And if we divide it by the number of intervals that we have, which is n, we're going to get each of the delta x's. And to make the delta x smaller, we just have more and more n's. And essentially, we're just going to let the n go to infinity, which lets our delta x go infinitely thin, and that allows us to calculate the exact area. So we're starting with this area approximation. The total area is this f prime times delta x, or in other words, this is our height, f prime times the width, which is our delta x. And we're going to let the delta x go to 0 by establishing an expression for delta x in terms of n, and then we're going to let the n go to infinity, so that delta x expression will tend to 0. So to be able to actually get an expression that we can use, we need to convert the f prime into a sigma notation expression. So how do we do this? So let's take a look at the simplest expression here. This is a simple linear expression, x plus 1. So we have a linear function with slope 1, a y-intercept of 1, and we're going to multiply that by dx to get each area, and we're going to integrate that. So if we start with our Riemann sum approximation, okay, our Riemann sum approximation is going to look like this. And what we need to do is we need to come up with an expression, an n expression for the x value and the delta x. Well, the delta x we've already done. We can just take the interval width. In this case, our interval width, again, I'll just highlight that. Our interval width is going to be from 0 to 4. And so we have our interval width equals 4. And we can work out our delta x value by taking that interval width of 4 and dividing it by n. So you can see that this expression then is going to show up in our sigma notation. So this part here represents our delta x. We also then need to have an expression for the height, or the f of x part. So we know that the f of x is going to be x plus 1. So we need to change that x expression in terms of n. So we have our limit going from, we're going to change the variable for k equals 1 all the way to the n value, some n value. And we're going to let the n go to infinity to have infinite number of rectangles. That part here, this portion here, then represents some expression that's going to represent the x expression in our function. Well, to get the x expression, we're going to need to figure out how to get x. So our x values of the height, we're going to use a plus. We're going to start at 0 and go plus delta x, plus delta x, plus delta x from the starting values. And this will give us left-hand Riemann sums, left-hand Riemann rectangles. So if I take the height here, actually this diagram's a little bit off in that we're going to get this rectangle here. It will be a right-hand rectangle. And we can get that value by starting at 0 and adding 4 over n for every k value. As we increase our k value from 1 to n, every time we increase k by 1, we're going to add one more delta x. And we're going to move along the line all the way to the n value. So this is going to represent our x variable, and we should check our bounds here because our n is going to go to infinity. So to check our start value, we can see that our n is infinity and our k is going to be 1. Okay, at k equals 1 and n equals infinity, our starting value is going to be 0. And then we can also check our ending value. Our n is infinity. For the n value, we're going to let n go to infinity, so that value is going to be infinity. So we end up, those are going to be a ratio of 1. So we end at an n value of 4. So we're going to then integrate starting at 0 and ending at 4. We can see that based on substituting our k and our n into those expressions. So then this value here represents each x coordinate. Okay, as we increase the k, we're just going to move along that line and find the height of the graph at each x coordinate. So that becomes our x coordinate. So I plug in here 4k over n, and then I now have my sigma notation expression that I can calculate the area with using the sums of those rectangles. Now, in this case, I'm going to need an infinite number of rectangles, which means we need to be able to have to actually do this, we need a formula to be able to sum up an infinite number of end values. So that can be done that's going to be done in a different video. So if you want to go to that, I'll put an extra link somewhere up here. So in the end, when I simplify this, my final sigma notation expression for this is gonna be this one here. We have the limit as n goes to infinity from k to n. The 4k over n represents the x expression. That plus 1 is my f of x, and my delta x is my 4 over n. And I can use this. I can still use this expression for any n value, but to make this an exact value, to go from the Riemann sum to the integral, I apply the limit. This gives me the actual integral value, which I should write down. So this is going to be equivalent to the integral from 0 to 4 of x plus 1 dx.